Good morning, Applied Physics students. This is Mrs. Krumschreider, and this is your teaching video for Chapter 5, Sections 1 and 2. Chapter 5 is about projectile motion, and the big idea in this chapter is that projectile motion can be described by the horizontal and vertical components of motion. Again, it's going to be important you remember or recall the difference between horizontal and vertical. So horizontal is left to right. Vertical is up and down. Okay, so remember that vertical is up and down and horizontal is left to right. So section 5.1 is titled Vector and Scalar Quantities, and it's really sort of a review. We talked about this before, about what vector and scalar quantities are. It is often easier to solve physics problems when you have a picture. And so you're going to see that I often am going to draw a picture before I solve a problem. And in physics, we often use some arrows, and they're used to represent the magnitude. Remember, magnitude has to do with the size and the direction of quantities or amounts. Okay, so these arrows, they are called a vector. So remember, we have vector quantities. And a vector quantity, actually I want to make this quantity. Requires both a magnitude or a size and a direction for a complete description. Again, you've learned so far that velocity is a vector quantity, as is acceleration, meaning they both need a size and a direction to be properly described. We also have what are known as scalar quantities. Remember, a scalar quantity can be completely described by magnitude alone or size. So they only need a size. For example, speed is a scalar quantity. And scalar quantities in some ways are a little bit easier for us to work with because they can be added, subtracted, multiplied, and divided like ordinary numbers, meaning there's nothing special to working with them. So like, ordinary So that's really all that was in this first section. It really was just that review about scalar and vector quantities. Section 5.2 is titled Velocity Vectors. So we're going to be talking about using those arrows to represent velocity. So the velocity of an object is often the result of combining two or more other velocities. So we're going to take a look at an example of that. We have an airplane, and this is my stick figure of an airplane. Okay, so there's my airplane. And my airplane is traveling 80 kilometers per hour due north. Okay. And there's a tailwind that is 20 kilometers per hour. Also going north, because tailwinds means it's pushing on the tail. So we want to know how fast this plane is actually traveling with respect to the ground. Well, a person on the ground, okay, is going to see this plane going 80 kilometers per hour plus the wind that's pushing it another 20 kilometers per hour, which results in, from the ground, the plane moving 100 kilometers per hour north. This is why, if you've ever flown on an airplane, that you might have arrived early. Okay, if you arrived early, somehow the wind was helping push and increase the speed of the plane. Or you might have arrived late, in which case the wind was acting in such a way that it was decreasing the speed of the plane. To look at another example, again, we're going to have a plane, but now the plane has turned around and is going the other direction. Okay, so it is now traveling 80 kilometers per hour due south. The wind, now would be considered a headwind, okay, is still pushing north at 20 kilometers per hour. So again, what we want to know is that person on the ground, how fast does that plane appear to be traveling? Right? And this time, the wind's going to slow this plane down. So the plane is traveling 80 kilometers per hour, and we're going to subtract the wind that's acting against it to give us a speed of 60 kilometers per hour, and it's going south. So this is that instance where the plane isn't traveling as fast as it would seem to be because of that wind slowing it down. And again, this works really well when we have parallel vectors. Okay? Because they're acting in the same direction or in 180 degree opposite directions. However, we also can use vectors. So vectors are also useful for combining velocities that are not parallel. So we'll take a look at an example. Here we have, again, we'll say it's a plane. Okay. And it is traveling 80 kilometers per hour due north. But this time there's kind of a crosswind acting on it. And so the wind is blowing from west to east. And the wind is blowing 60 kilometers per hour. So this is our wind. Don't know how to draw wind. Okay. So how can I figure out the velocity of this plane? So what I do is I am going to draw my vectors. They still have to be pointing the correct direction, so I have to be going north on this one and east on this one on my wind. Now, the resultant, so the path and the speed that this plane would actually travel, okay, is found by, we kind of make a square or a rectangle. And the resultant is this middle. So this is what's called the resultant. And it really is the sum of these two vectors. So, the resultant of two perpendicular vectors is the diagonal of a rectangle constructed or made of with the two vectors as sides. So what I mean by that is this vector, this side of the rectangle, and this side are the same length. And this side of my rectangle and this side of my rectangle are the same length. Okay? So that's what we mean. And they're perpendicular. Remember, perpendicular means that they form a right angle. Okay? So remember that perpendicular means a right angle. So this is how we kind of draw this. But mathematically, how do we figure out that number? Well, you're going to use a little geometry. You're going to use the Pythagorean theorem. Now, hopefully you've learned this before, that this is where you have a side. And in our case, I'm going to kind of put them in different colors to kind of help you picture what's happening. Right? We're talking about vectors like this. So we have the other side of this that's equal to that orange one vector, and the other side of this rectangle, which is equal to, okay, my green vector. And, okay, in the Pythagorean theorem, this is, one of our sides is A. The other one of our sides is B. And remember, okay, you're forming a triangle here. So this resultant, okay, this is C. And in that equation then, C squared equals A squared plus B squared. So if I'm trying to figure out just that resultant, because remember, we're calling this in physics, this is our resultant. To find C, we're going to take the square root of A squared plus B squared. So, if this isn't something you're familiar with, then you definitely need to make sure you have this written down in your notes. So we will be using this in just a couple minutes when we start to look at some problems. So we're going to look at some problems. Our first problem is, how fast would an airplane move over the ground if it had an airspeed of 100 kilometers per hour when flying into a strong gale, which is just another name for wind, of 100 kilometers per hour. So again, I like a picture. So it doesn't really matter which way we have our plane flying. So I'm going to kind of put it flying east. And remember, it's going 100 kilometers per hour. But there is also a wind acting that is 100 kilometers per hour. So these are my vectors. I have my arrows here. What am I going to do mathematically to figure out the resultant? Right? These are in opposite directions. So it's 100 kilometers per hour that the plane is traveling minus the 100 kilometers per hour that the wind is pushing, which gives me 0 kilometers per hour. So on the ground, it would appear that the plane is not moving. Okay, from the perspective or relative to the earth, the plane is not moving. There is no ground speed. Probably don't want to be on that plane. It's going to make for an awfully long ride. All right, let's look at another problem. How fast will a boat that normally travels, 10 kilometers per hour in still water, be moving with respect to the land if it sails directly across a stream that flows at 10 kilometers per hour. So again, if we kind of look at a picture, right, here's my stream, and there's water moving in it, right, and that water is moving 10 kilometers per hour. And then I have my boat, and my boat's going to cross that stream going 10 kilometers per hour. So this is one of those ones where I'm going to build a rectangle, right? I have my boat going 10 kilometers per hour across the stream, and I have the water moving 10 kilometers per hour. So again, I'm going to make my rectangle, and here's my resultant velocity. So in terms of direction, if we call this north and we call this east, we can tell already that the direction of my velocity is definitely going to be northeast. Okay? Now, how do I get my number? Right? This is that a squared equals b squared equals c squared. So to find my resultant, which is my c, I'm going to do the square root of a squared plus b squared. A is 10 kilometers per hour squared. B is 10 kilometers per hour squared. Right? So that's the square root of 100 plus 100. So I'm doing the square root of 200, which is equal to 14.14 kilometers per hour. So that stream increases the speed at which that boat crosses the stream. The last thing we're going to take a look at is our page 71 think question. Suppose that an airplane normally flying at 80 kilometers per hour encounters wind at a right angle to its forward motion, a crosswind. Will the airplane fly faster or slower than 80 kilometers per hour? Well, we could kind of use this example to answer that, right? We see that the resultant here is faster than either of the sides. So we can kind of guess based on that, but we also can kind of show with some math, right? So again, we have an airplane, okay, flying, and again, 80 kilometers per hour. And it encounters a wind at a right angle from its forward motion. So here's my wind. Okay. And let's even say it's not a very big wind. Let's say it's just 10 kilometers per hour. We want to know what happens to its speed, right? So this is that Pythagorean theorem again. We have 80 kilometers per hour. We have 10 kilometers per hour. I make my rectangle. Here's my resultant. Now I can kind of look at it and tell it's probably longer. And to figure out that number, remember I'm going to do the square root of 80 kilometers per hour squared plus 10 kilometers per hour squared, and then take my square root of that value. And when you do that, you should get about 80.62 kilometers per hour. So as we sort of said, based on our previous problem, it's going to make the airplane fly faster than 80 kilometers per hour. So that brings us to the end of sections 1 and 2. Have a good day. I'll talk to you tomorrow.